Welcome to General Chemistry 1. Let's talk about kinetic molecular theory in this video. From the name kinetic, it means moving. So we're talking about gases that moves at a molecular level in this video. First, what is the origin of pressure? Imagine we have this setup, experimental setup. Before we have any gas in the bottom part, the plug sits in the bottom. After we have gas in the bottom, then the gas moves this plug up in the middle. So what is the driving force to move this plug? Well, if you think about that, because of the gas, then the plug is moved. So it's the pressure of the gas inside of this container that moves this plug. So why exactly does it happen? Why the pressure of the gas can move this plug? If you look at the micro scale, which means you are looking at each gas molecule, and we have thousands of these gas molecules in the container. Okay, each of the gas molecules moves freely in the container, and when it moves freely, very likely it will eventually hit the chamber wall or hit the wall of the container. When you have thousands of these molecules hit the wall of the container, we're creating a force, and correspondingly, we're creating the pressure. So in microscale, pressure comes from the force generated by freely movable gas molecules hitting walls of a container. Okay, so in this video, all the concepts will be based on microscale points of view. So we're really looking at these gas molecules individually. Now, kinetic molecular theory is actually the model that accounts for microscopic gas behavior at the level of individual particles. Particles means atoms or molecules. So this is the theory that explains things while you observe in your experiments or your daily life. Okay, but we'll explain these phenomena at the molecular level. There are a few postulates of kinetic molecular theory. So first, particle volume is assumed to be zero. It's like those, conditions for the ideal gas laws, ideal gas. The same thing for the kinetic molecular theory, particle volume is assumed to be zero, and particles are in constant random straight line motion, except when they collide. Okay, when they collide, the collisions of particles are elastic, which means no energy loss during collision, no intermolecular attractive or repulsive forces. So these postulates of molecular kinetic theory is just help you to understand the theory. Okay, so we can use the kinetic molecular theory to explain all the individual gas laws we described before. For Boyle's laws, it says pressure and volume. When pressure times the volume, we have a constant. So, and that's under the condition of the same temperature and same amount of the gas molecules inside. So imagine we have a increase of pressure. Okay. So if we have increase of pressure, that means we have more frequent gas molecules hitting the wall. So in that sense, we need to decrease the volume so we can decrease the surface area of this container that holds gas. So there's more chances the gas molecules can hit a wall within a certain time. In other words, if we shrink the volume, the gas molecules will travel less distance before it hits a wall. So the frequency of hitting a wall increases and pressure increases. For Chelsea's law, volume over temperature is a constant. So again, here we have this device. There's a plug. We trap some gas in the bottom part. And when pressure increases, these gas molecules will move freely and at a higher speed. Okay, when they move at a higher speed, they hit the wall more, like hit the wall stronger than before, and that will increase. That will try to that will be the driving force to move this plug to the higher position to maintain the same pressure. Okay, so then in this case, the volume will increase accordingly. And for the Dalton's law, where we have the partial pressure, total pressure equals to the sum of the partial pressure. That's also easy to understand. If we have one type of gas molecule hitting the wall, we only have these amount of hits per second, right, per area. But if we have more gases inside, okay, then the chances of two different types of gas molecules hitting the wall increases, and we can treat that as the net effect will be the sum of this the two individual type of gases. Okay, so total pressure equals to the sum of the individual gas pressures. Okay, so with kinetic molecular theory, we're looking at gas at molecular level, but usually the gas molecules are thousands and hundreds. There's so many of them. So we need to have a little bit idea statistically how these gas behave. Okay, now we're going to show you a few plots, and that's the statistic of how these gas as a group behave on the different pressure and temperature. So let's take a look at those. So the first concept is the most probable speed. Now I'm going to show you a plot. In the x-axis, that's the speed of one gas particle, in this case, nitrogen molecule. And in the y, that's how many nitrogen molecules are at a certain speed. So we can have this plot, just take one of them at this moment. So look at these blue ones. So the peak of this diagram shows the most amount of nitrogen molecules, the speed that the most amount of nitrogen molecules are at. Okay, so if you read this peak position in the x, that gives you the most probable speed. That's how we define the most probable speed from this diagram. So each particle or gas molecule has a molecular speed u. They may be the same, they may not be the same, but each of them have its own u. The most probable speed, by definition, is the speed of the most particles, and that's the peak of each peak of each curve here, with the number of particles versus the speed of each molecules. From this diagram, we have several other plots. Those are the plots taken with the same gas at different temperatures. So when we change from room temperature 270 or 0 degrees C or 273 Kelvin to higher temperature 1273 K, you can see the most probable speed increases. That means the speed of most particles increases. You can understand that it's like everything gets hotter, everything is more energetic, they want to travel at faster speed. So the whole plot shifts to a higher speed, and also the most probable speed increases. If you further increase the speed to 2273 Kelvin, you can see the most probable speed keep increasing to a higher level. Okay. At the same time, these curves flattened, right? So it's not a linear shift for everyone. The distribution follows the way that when the most probable speed increases because of a temperature, the curve flattens out. So from this diagram, we know when temperature increases, the most probable speed increases. Okay, so most probable speed talks about just the speed, the rate. We can get If we know what type of molecule it is, we can calculate the kinetic energy, the energy of movement, right? The kinetic energy of a certain particle. And also we can get the average kinetic energy of the whole gas. So let's take a look at that. In this diagram, again, we have the y as the relative number of molecules at a given speed. The x-axis is the molecular speed, and at a given temperature, we don't change temperatures here. So it's speed at given temperature in the x. You can tell there are different diagrams here in this plot, and that corresponding to different type of gases. If we compare oxygen and hydrogen, the molecular weight of oxygen is 32. The molecular weight of hydrogen is 2. So oxygen is heavier than hydrogen. For the molecules, for the gas that is heavier, have a larger molar mass, the most probable speed, the peak of this diagram, is smaller than hydrogen, that of the hydrogen. So at a given temperature, larger the molecular weight, the smaller the most probable speed. Okay, and for each particles, each data point here in this plot, for each particles, we can calculate the kinetic energy, EK, that equals to half times mass times the square of the speed, of that speed, right? So for each data point here of the plot, we can calculate the kinetic energy of that specific molecule, right? And we have so many molecules here, so we can get the statistic value, the average kinetic energy. So, and that comes to the most interesting part. When we calculate the average kinetic energy, all gases at the same temperature have the same average kinetic energy. The kinetic energy for individual gas may be different, but you count everything together, the average are the same. Okay, so average kinetic energy only depends on temperature. We can write the equation here. EK bar, that bar on top of EK means the average, equals to 3/2 times R over Avogadro's number times T. So from this equation, you can tell that the average kinetic energy is only dependent on the temperature. And we can use another equation to explain that. So another way to express average kinetic energy is that equals to half times the m, the mass of a particle, or the molar mass of a particle, that times the average of the squares of molecular speed. Okay, so you do the square first and then do the average. So in this equation, you can tell at a certain temperature, the kinetic energy is fixed. The bigger the mass of a particle, the smaller the average of squares of the molecular speed. Okay, so in general, you can see at certain temperature, the bigger the molecular weight, the smaller the average of the speed is. So this is the concept of average kinetic energy. You need to know these two equations and know which, use these two equations to explain a few phenomena. Okay. Finally, we would like to talk about root mean square speed. We mentioned that there are two ways to express average kinetic energy. If we link them together, we can get the U, okay, U, we call that URMS, root mean square speed. Okay, that root mean square speed equals to square root 3RT over molecular mass. Okay, molecular mass over a gas particle. And in order to calculate the root mean square speed, we need to pay attention to the unit sets. So if you want to get the meter per second of root mean square speed, then we need to make sure R should have a unit of joule per mole per Kelvin, T should have a unit of Kelvin, and molecular mass should have a unit of kilograms. Okay, kilograms per mole, not grams per mole. All right. We talk about Nanny speed here. I want to show you in the plot the relative position. Okay, so now we have, imagine we have a gas and it has a plot like this. The y-axis is the number of molecules with a given speed. The x is the molecular speed. Okay, so we know for the most probable speed, U sub p, that's the peak of this diagram. Okay, that's the speed that most particles are at. Now, we also talk about the average speed. Okay, average speed is, count the speed of all molecules and take an average of that. Average speed is actually a little bit higher than the most probable speed. So it's not at the peak, a little bit right to the peak where we have a higher speed. That average speed is different from the root mean square speed. Okay, so if we plot the root mean square speed in the diagram, it's even higher than average speed. So it's the most right one. The plot I show here just want to demonstrate that these three speeds are different. They are not the same one on the plot. Okay, now with the kinetic molecular theory, let's try a few questions. True or false? First, at 500 Kelvin, a hydrogen gas molecule must have a higher speed than an oxygen molecule. Well, for this question, it is false. Okay, we can say 500 Kelvin, the most probable speed for hydrogen is higher. You can see here, the lighter the molecule, the higher the most probable speed. However, for certain gas, we're not talking about the statistic value. We're talking about an individual gas molecule. We don't know. For example, we can have hydrogen gas with very, very low speed, but we can also have oxygen molecule at higher speed than that of hydrogen. So when you compare each individual of gas, we don't know. We don't have a good answer for it. It may or may not be higher, but we just don't know. Yeah. Second, at 500 Kelvin, the average kinetic energy of hydrogen gas and oxygen gas must be equal. For this question, the answer is true. Remember, the average kinetic energy only depends on temperature. So since the both gases are at 500 Kelvin, they share the same average kinetic energy. Third, at 500 Kelvin, the root mean square speed of nitrogen gas is the peak of the corresponding speed distribution diagram. This one is false. So if we want to read the peak is the most probable speed. Okay, it does not matter what temperature you're at, the peak is the most probable speed. And the root mean square speed is on the right of that most probable speed, as I showed in the previous slides. All right, this is the end of the kinetic molecular theory. I know there are many equations here. For those equations highlighted in red, you need to understand and know them. For others, it's just for your reference. You don't need to really have a very deep understanding of those, just help you to understand the concept. So this is the end of the video, and I'll see you next time.